Hi, this is Alfozia Nihar from At Home Tuition. Welcome to our session today. The topic that we're going to discuss in our today's video is definite integrals of piecewise defined functions. Hope you all know that function is nothing but a rule which actually associates an input to a particular output. Functions have various representation. One way of representing a function is a graph. Actually, a graph tells us which input is associated with a particular output. In calculus, it is common to express functions in terms of formulas. Many functions actually which arise in practice cannot be described by a single formula. Hope you all know that too. In these cases, what we would do? We can often benefit by defining a function piecewise. A piecewise defined function tells us which rule to follow under specific circumstances. Here in this example, g is a function which has a rule. It squares if x lies in between 2 and -2, and the input changes its signs and we add 6 if x is greater than 2. Otherwise, for all the condition, I mean x is less than -2, the output is going to be 4. So this is what this function is saying us. Oftentimes, piecewise defined functions can be integrated. In order to evaluate these integrals, we use property. In this video, we are going to see how to evaluate and graph piecewise defined functions, and also how to evaluate and graph the greatest integer or floor function. A piecewise defined function applies different rules, usually as formulas, to disjoint subset of its domain. Disjoint means non-overlapping. Domain means you can also include the subdomains. To evaluate such a function at a particular input value, we need to figure out which rule applies here. And to graph such a function, we need to know how to graph the pieces that correspond to a different rule on their subdomains. The greater integer, or you can also call it as floor function, and its graph you can see that in both calculus and also in computer science. Both will be exhibiting the same feature, very similar features. Now we are going to take the absolute value function. Let f of x is equal to absolute value of x. We discussed that the absolute value function f can be defined as a piecewise function. So the piecewise defined of the function f can be given as f of x can be defined as x if x is greater than or equal to 0, or it can be defined as negative x in case if x is less than 0. For instance, you can take some number in the place of x. Let me take 3. F of 3 is equal to absolute value of 3, which is nothing but 3, because 3 is a number which is greater than or equal to 0. Am I right? 3 cannot be a number less than 0. So you can say that f of 3 is nothing but 3, because we are going to use the top rule, which applies to the subdomain 0 to infinity. What is the subdomain for this one? It starts from 0 and ends at infinity. All the positive numbers. Am I right? Okay. What will happen if I take -3 in the place of x? However, f of -3 can be written as absolute value of -3, which is nothing but negative of -3, which is equal to 3, because -3 is less than 0. Am I right? And we use the bottom rule, which applies to the subdomain. It starts from -infinity to 0, the left side of the number line. Hope you're clear with this one. Let us draw the graph for this one. Do you see this graph? This is the y-axis, and here it is 3. And on the x-axis, you can just draw a line that will be 3 and -3. We say that f is continuous at 0. That is, if we trace the graph of the function f of x with a pencil in the point 0, 0, we do not have to lift our pencil, right? It will be very continuous. So we will provide a formal definition of continuity in the upcoming videos. So for this one, the piecewise defined functions are often discontinuous. We all know that. They lose continuity where they switch the rules. But here this graph is continuous at 0. Hope you're clear with this point. Now let's see what is evaluating piecewise defined functions. Now let's see few examples on evaluating piecewise defined function. Here is the first example. Let the function f of x can be defined by x square when x lies in between -2 and 1, and the function is defined by x plus 1 when 1 less than or equal to x less than or equal to 2. Now let us evaluate for negative 1 and 1. Also we can take f of 10. I'm going to take 3 numbers. To evaluate f of negative 1, we are going to use the top rule. Since f of negative 1 when x is equal to 1, x is a number 1 which lies in between this limit, right? So we are going to use the top row. So negative 1 will lie in between negative 2 and 1. So f of negative 1 is nothing but the square, negative 1 the whole square, which is equal to 1. So whenever you get something like this, you can just plug in that number on a number line and check where that point lies in between. So from that you can understand which interval the number is lying in between. So here, if I draw a number line and mark all these numbers, this will be one group and this will be one of the set. And negative 1 is a number that lies in between these two. That's why I chose the top rule. And I'm squaring the value, I'll get 1. Same way, if I wanted to evaluate f of 1. To evaluate f of 1, I'm going to use the bottom rule. Since 1 lies in between this thing, 1 or 2. So we are going to use the bottom rule. Bottom rule is x plus 1. So this is going to be 1 plus 1, which is equal to 2. Does this make sense to you so far? In case if you are supposed to find or evaluate f of 10, what we will do? If you plug in this a 10 value in between these two intervals, actually there is no rule for x is equal to 10. Am I right? So this is going to be undefined because we have no rule defined here for x is equal to 10. And 10 is not in the domain of the function f of x. It starts from negative 2 and ends at 2. There is no other thing. There is no number included in the domain. So this number does not fall in the given domain. So we can say that f of 10 is undefined. So whenever you are saying some function is undefined, you should also know to explain. You should also support your answer by a proper explanation. So here I am saying that the number is not in the domain of the function f of x. Hope you understand the reason why we say that some function falls in the domain and some does not fall in the domain. And you should know which rule to follow. You have to know how to switch the rule according to the number given when you are asked to find or evaluate a piecewise different function. Here is another example. Sometimes you will be given piecewise functions and asked to evaluate them. In other words, find the y values when you are given an x value. So let's do this for x is equal to negative 6 and x is equal to 4. We are not going to use the graph here. Here is the function. We first want to look at the conditions at the right first to see where our x is. When x is equal to negative 6, we know that it's less than negative 2. So we plug it in our x to 2x plus 8 only. So f of x or y, whatever. So 2 times negative 6 plus 8. This will give you negative 4. We don't even care about x square here. So it's that easy. You can also see that we did this correctly by using the graph also. If you are given a graph, it will be very easy for you to do this. Okay, let's now try for x is equal to 4. We look at the right first. You should also look at the rule which is applicable, because only if you know where the x value lies in between, only then you can pick the rule that is applicable or suitable. So see that our x is greater than negative 2. So we are going to plug that in x square. For whatever number greater than negative 2, we have to use this rule. In a previous example, x lies in between two numbers, but here they are just saying that x is less than or equal to negative 2 or greater than some number. So here we are going to plug this x value in this rule, x square. So here in this case, for this part, you can just ignore the first rule. So f of x or y, whatever, is x square. So just do the square of 4. 4 square is 16. So choose the rule accordingly. You should know what rule should use when the x values lies in between certain interval. You will be asked to graph the piecewise function, and you have to tell if the piecewise function is continuous or not continuous by just looking at the boundary points. When the graph is given, we can obtain the equations of line. You can find the equations from the graph. And when it comes to an absolute value as a piecewise function, as we taught earlier, Notice that we can get a turning point or a boundary point by setting whatever is inside the absolute value to x. Then we will either use the original function or negate the function depending on the sign of the function without the absolute value in that interval. Hope you're clear with all the points we discussed in today's session. We can talk about graphing, obtaining an equation, and finding whether the given function is continuous or not in our upcoming videos. In case if you have any query regarding this video, please let me know. See you in the next video. Have a great